All right, I'm going to continue the lecture now by talking about a subject that will tie into the results in the previous lecture where we discussed Yasuda's work on ion transport through hydrogel polymers, and almost all of Yasuda's work was on hydrogel polymers that were uncharged. And today I'd like to switch the topic to talk about ion transport through charged polymers and to show you the difference between ion solubility and ion diffusion in materials that are charged and uncharged. This is important in applications like controlled delivery of charged drugs from hydrogels, and in water purification applications like electrodialysis, and also in some cases potentially reverse osmosis membranes. And so we will start by considering two classes of membrane processes. And one I'll call the osmotic processes, and these are cases where there's no electric field and the transport of water anions is driven by pressure and concentration gradients. So this would be an example of this would be reverse osmosis to desalinate water. Membranes in this case may or may not have fixed charge groups, that is, they may or may not be charged. The other case is the so-called dialysis processes, and here the membranes necessarily have charge groups on the polymer backbone, and the driving force is an electric potential, and as a result of ion transport, an electric current flows. In the osmotic processes, generally the objective is to permeate water and also as few ions as possible if you think about using something like reverse osmosis to do seawater desalination. In the dialysis processes, we're often trying to do the opposite, that is, permeate some ions and as little water as possible. I'll show you examples of both here in just a moment. So osmosis and reverse osmosis are quite closely related. You'll probably remember perhaps from high school the classic osmosis experiment where you have a membrane like shown here at the bottom of this slide, that separates a solution that contains salt water. The little yellow dots here represent a solute, could be salt or other solute like sugar, almost any molecule that dilutes the water. And so you have a membrane that's selective for the water, but doesn't want to yet let the yellow solute through it. On the other side of the membrane, on the right-hand side, we have only pure water. And what will naturally happen is on the left-hand side of this membrane, the water concentration is lower than it is on the right-hand side. And so that difference in water concentration sets up a driving force to drive water across the membrane from right to left. And this is the process that you would know as osmosis. This is how trees get water into their roots and then up into the leaves and so forth. It's the way simple biological osmosis works. And if we were to plot for a given value of solute concentration, the amount of water flux that would come across this membrane, we would be at the bottom part of this graph. So we would have water flux from right to left at a rate that would be determined by the water permeability of this membrane and the essentially difference in activity, thermodynamic activity of water from the right-hand side to the left-hand side. Now, if we start to apply a hydrostatic pressure on this left-hand chamber, and the pressure, the hydrostatic pressure on that chamber is greater than it is on the right-hand side, that pressure difference can cause a flow of water or a flux of water that goes from left to right. And we're going to talk about this a little bit more when we discuss how pressure difference induces solute transport like water. But suffice it to say that the greater is the pressure on the left-hand side, the greater is the flux of water from left to right. So the concentration gradient drives water right to left, the pressure gradient drives water left to right. And what's being plotted in this graph is water flux as a function of the delta P across the membrane. That is the difference between the pressure on the left-hand side and the pressure on the right-hand side. And the greater that pressure difference is, the lower is the water flux. That is, the water flux driven by pressure from left to right starts to offset the osmotic flux of water from right to left. And there will come a delta P where the net water flux across the membrane is equal to 0. And this is the point where the water flux due to the pressure difference is exactly offsetting the water flux due to the concentration of solute on the left-hand side of the membrane. And if we continue then to increase the pressure on the left-hand side of the membrane, we start now to have a net driving force for water to go from left to right. That is, for water to pass from the low concentration side of this membrane to the high concentration side. And this is the regime that we know as reverse osmosis. That is, the water flow is opposite to what it is in standard concentration-driven osmotic flow. And the pressure difference where the water flux is exactly equal to 0 is corresponds to what's called the osmotic pressure in the solution, or more correctly, the difference in the osmotic pressure between the left and right-hand side of this membrane. The osmotic pressure is defined very generally from thermodynamics as essentially a measure of the thermodynamic activity of water in a solution. R and T are the gas constant and absolute temperature. VW bar is the partial molar volume of water, which is almost always close to the molar volume, that is 18 cc's per mole. In ideal solution thermodynamics, this term can be written as the salt concentration. If we now have think about this solute as being a salt, as the salt concentration in the water on the left-hand side times RT. This derivation can then be applied either to the left or right-hand side, and if there's no salt on the right-hand side, then delta pi is just equal to the osmotic pressure on the left-hand side of the membrane. And so this is the phenomenon of a conventional osmosis, where one can use this phenomena by applying a high pressure to a saltwater solution to drive water across the membrane under essentially concentration gradient and free it from the salt that's in the original solution. And this is a technology that's used widely for reverse osmosis desalination, for example, of seawater. And the reason we use reverse osmosis is shown on the right-hand side. There's one can desalinate water by just distilling salt water to evaporate the water and then condense it, but this comes at enormous energetic cost. There are ways to improve that by heat recovery in the distillation process, but the reverse osmosis technology gives energy costs that are well below those of evaporation-based technologies, and as a result, reverse osmosis membrane separation of seawater has come to dominate the industrial application in this space. And also show there is a theoretical minimum energy associated with making a separation, and I show that in these units of kilowatt hours per cubic meter to show you how close the reverse osmosis is to that thermodynamic limit. Now, the previous slide talked about concentration-driven separation of water from ions. This will talk about electric field-driven separation, and we'll use the example of electrodialysis to illustrate that. And so, in an electrodialysis cell, there are membranes. They're typically flat sheet membranes that are stacked together with spacers between them for water to flow between those spacers. And often there'll be hundreds of these membranes in a stack, and there's then electrodes placed on either side of that, either end of that stack. And the membranes are now special. They have fixed charges on the backbone of the polymer. Those that have negative charges on the backbone are referred to cation exchange membranes because these negative charges will attract cations or positively charged ions. Those that have positively charged ions on the polymer backbone are called anion exchange membranes because those positive charges will attract anions or negatively charged ions. And so the way electrodialysis works is that a saltwater feed is passed through each of the channels between alternating cation and anion separation membranes, and then an electric field is applied across these electrodes. And so the cations are trying to move the cations are trying to move from left to right towards a negatively charged cathode, and those cations can go easily through the oppositely charged cation exchange membrane. In fact, that's why it's called a cation exchange membrane, is because it can readily move cations from one side of the membrane to the other. These negative fixed charges like cations, and so will attract cations into the membrane. On the other hand, the cations are rejected from the anion exchange membranes. Having this positive charge in the anion exchange membranes acts to inhibit the sorption and then transport of cations through these membranes by a process known as Donnan screening, which we'll talk about in a moment. But you can think about it simply as opposite charged ions attract, and so the cations want to go into the cation exchange membrane. The same charge ions repel one another, so the cations are repulsed from the anion exchange membrane. Now, at the same time, the anions are trying to work their way from right to left to get to the positively charged anode, and they can go readily through the anion exchange membrane because they have opposite charge to the charge on the backbone of the polymer, that is the anion exchange membrane, but they're rejected from the cation exchange membrane. And so as this process goes along, you wind up with salt, mixtures of cations and anions concentrated in alternating compartments of this device. And then in the other compartments, that is the ones that appear empty now, will be depleted in ions. And so if you're looking to make purified water by this process, that shows up in these channels and comes out as a so-called diluate stream. And the saltwater feed is concentrated in the alternating channels and is taken off as the concentrate stream. You'll notice that this method of purifying water works somewhat differently from the reverse osmosis shown in the previous slide, in that what's being done is one is actually moving the ions rather than moving the water. Now, the ions take some water with them because they're hydrated, but the idea in this case is to use electrical energy to cause the ions to migrate with as little water as possible. Typically, historically, I would say, this approach to desalination works at low concentrations of salt. That is, it's more energy efficient at low concentration of salt to take the salt out of the water than it is to take the water away from the salt. At high concentrations of salt, like in seawater desalination, historically it's been more energy efficient to remove the water and leave the salt behind. And so this process requires alternating membranes that are negatively and positively charged, so it requires both cation and anion exchange membranes. And this will be the types of membranes we'll talk about in the lecture today. The way that we describe ion transport under either concentration gradient or an electric field gradient is typically through the so-called Nernst-Planck description, and I'll write that here for monovalent ion transport. And the Nernst-Planck description says that the flux of an ion through a membrane depends upon the diffusion coefficient of the ion through the membrane. And if there's a concentration gradient of ions across the membrane, then there can be a flux of ions driven by the concentration gradient. If there's an electric potential gradient, that can also drive the flux of ions across the membrane. Here, Zi is the valence of the ion, F is the Faraday constant, Cim is the concentration of ion I in the membrane. Now in the laboratory, we can do two extreme experiments to isolate either the concentration gradient driving force or the electric potential driving force. And so we're going to talk about that in some of the experimental data today. One experiment we can do is similar to the osmosis experiment, and that is we put a membrane sandwich it between two aqueous solutions, one which has concentration of salt. CSS is the concentration of salt in solution. And then on the right-hand side, the solution is initially free of salt. And this establishes a concentration gradient in salt to go from left to right. And if you monitor the ionic conductivity of the electrical conductivity of the solution in the receiving cell, the one that's initially free of salt, that conductivity rises over time as salt permeates through the membrane, and you can use that information to calculate the so-called salt permeability coefficient of that membrane. And in this case, where you have only a concentration gradient driving salt transport, there's no electrical gradient. Now, like in the osmosis case, there will be a flux of water in the opposite direction, and we're not going to worry about that right now. We'll focus on the ion transport. Now, you can apply the Nernst-Planck equation to this case with these field-driven terms set to be no net electric field across the membrane, and you get an expression for the so-called salt permeability that is shown here. And it relies on, or deriving this expression relies on the fact that a really important, fundamental, and very powerful force in electrochemistry is the concept of electroneutrality. Nature simply will not allow much of a charge imbalance to build up in either of these solutions or inside the membrane. And what that means from a practical point of view is that, for example, if we consider the positively charged ion to be a sodium and the negatively charged ion to be a chloride, so just dissolving a little bit of table salt in this left-hand side solution, what it means to be electroneutral transport is that every time a sodium ion goes through this membrane, a chloride has to go with it so that you maintain electroneutrality in the solutions and in the membrane. And that concept of electroneutrality means that the rates of transport of cations and anions through the membrane are intimately coupled to one another. And so with that in mind, you could derive the expression that is shown here, and it relates the so-called salt permeability, which is just the flux of ions through the membrane times its thickness divided by this concentration of salt across the membrane. That salt permeability is equal to the product of the salt partition coefficient in the membranes times the so-called salt diffusion coefficient in the membrane. So this looks exactly like the expression that we use to describe gas transport through polymer membranes, where we said that P is equal to D times S. Here in the aqueous and salt world, the nomenclature grew up somewhat differently, and so instead of saying that P is equal to D times S, we say that P is equal to D times K, where K is the solubility or partition coefficient of salt into the membrane. Now, this salt diffusion coefficient through the electrostatic coupling given by electroneutrality, that is that for every cation that comes across, an anion has to come with it for monovalent ion transport. The salt diffusion coefficient depends on both the diffusion coefficient of the cation as well as the anion in the membrane. Superscript membrane is always going to be the variables inside the membrane, and it depends as well on the concentration of cations and anions in the membrane. This last term is getting at the salt solubility or salt partition coefficient, and it's just how fast the concentration of so-called co-ions, in this case anions, change with salt concentration. We'll come back to that a bit in a moment. Now, another experiment that we can do in the lab that isolates now electric field-driven transport is shown here. So we use a very similar setup to the one on the right, except now the concentration of salt is the same on both sides of the membrane, and we have electrodes in the cell. And when we apply an electric potential, the cations want to migrate towards the negatively charged electrode, and the anions want to migrate towards the positively charged electrode. And if we use the Nernst-Planck description now to describe this experiment, and again maintaining electroneutrality, we calculate the so-called ionic conductivity, kappa, and it is closely related to the permeability, except now this is a measure of the current required to move these ions back and forth across the membrane. F is the Faraday constant, R and T are the gas constant and temperature, and then these are the diffusion coefficients of the cations and anions in the membrane, as well as their concentration in the membrane. And so what you can see is that both the salt permeability and the ionic conductivity, that is concentration-driven transport and electric field-driven transport, depend intimately on the diffusion coefficients of the ions in the membrane and the concentrations of ions dissolved in the membrane. But they have different mathematical forms, and that turns out to be important for us later. So if we have a fundamental model that predicts how ions partition into membranes and then how they diffuse through membranes, we can predict both the results of this electric field-driven experiment, which is common in electrodialysis, as well as the results of this concentration gradient-driven experiment, which is used in applications like osmosis and reverse osmosis. And so it makes sense that the flux of ions is driven by a gradient in electrochemical potential, which includes both concentration gradients and the possibility of electric field driven transport. And so from this fundamental picture, we can describe both of these experiments. And the mainline point here is that both permeability and conductivity depend on ion concentrations and diffusion coefficients in the membrane. Now we're going to be looking at data as a function of salt concentration, and we'll use a scale of salinity that goes from about 0.01 to 1 molar. And there are other concentration ranges that might be useful for certain applications. This one is convenient for example, for desalination of water, and so I show what the salt concentrations are in weight percent and in parts per million, as well as in molar seawater. Just to orient you, is about 33,000 parts per million. It varies from place to place in the world. So what we would call brackish water is often on the order of 1,000 to 2,000 parts per million. Now, the slide showing how ion permeability and ionic conductivity are related to the salt diffusion coefficients in the membrane and the salt concentrations in the membrane leads us naturally to explore how ions partition into charged polymers, and that is ion solubility or ion sorption in charged polymers, and then later we'll talk about ion diffusion, and after that put this picture together to give expressions for both ion permeability as well as ionic conductivity through such membranes. To focus this discussion a bit, we're going to talk about the properties of commercial ion exchange membranes. So the membranes that are shown here, or their chemical structures, are used in electrodialysis membranes. And the ones that are shown on this page are cation exchange membranes because they have these negatively charged sulfonate groups bound to the backbone of the polymer chain. And all these sulfonate groups need a positively charged cation to electrically balance them. These materials are always cross-linked, so this would be a copolymer of styrene cross-linked with divinyl benzene, and then some of the styrenes are sulfonated. Now, this picture is not exactly anatomically correct because of the membranes, the way the membranes are used commercially, only about I think about 35 mol% of these styrenes are actually sulfonated. These materials are formed into flat sheet membranes. This is their CR61 is the trade name given to them, and I'm going to refer to it as a styrenic CEM or STCEM. Styrenic to denote the aromatic backbone, and CEM to denote that it has this negatively charged sulfonate group. Its cousin here has an acrylic backbone, and so I'm going to denote it by AC-CEM. these sulfonate groups are very strongly acidic groups, and so at virtually any pH you could imagine, they're always fully ionized. The ion exchange capacity, or IEC, tells the number of millimoles of the charged groups per gram of dry polymer, and it's similar in these materials. These membranes are rather thick, actually, 600 microns. Others used for electrodialysis may be as thin as about 100 microns. Now, this slide shows anion exchange commercial membranes, and these look an awful lot like the cation exchange membranes, except instead of having sulfonate groups coming off the styrene, they have quaternary ammonium groups, and this group, the trimethyl quaternary ammonium group, is a very basic group, and it is essentially charged at all pHs of interest, and so it's fully ionized when it's used for water purification. And again, there are styrenic AEMs and acrylic AEMs, and so I'll refer to these as ST-AEM and AC-AEM. And again, their ion exchange capacities are in the same ballpark as those of their cation exchange analogs. In electrodialysis membrane, you always have, for every cation exchange membrane, you have to have it paired with an anion exchange membrane, and they're stacked together. So this is the chemical structure of the membranes that we'll look at, and these are ubiquitous in electrodialysis and ion exchange membranes. One of the most important characteristics that governs transport in such membranes is the water uptake. It turns out to be very important for both ion sorption as well as ion diffusion. You'll remember that Yasuda postulated that the water content in his uncharged membranes was proportional to free volume, and he correlated the salt transport over 5 orders of magnitude in diffusion coefficient simply with water uptake. So we'll measure water uptake almost before any other property when we're seeking to do fundamental studies on ion exchange membranes. And the water uptake of the membranes that I've just shown you are shown here, and I don't want to make a whole lot of emphasis about the exact values of water uptake. It would take further discussion and knowledge of the chemical structure to relate this water uptake, for example, to chi parameters and to cross-link densities, and we will not be doing that here. Suffice it to say that the water uptake levels are pretty substantial in these membranes. The units on this are grams of water per grams of dry membrane, and some of these materials are taking up nearly their own weight in water. Not all of them, but some of them are. Now, these are representative ion exchange membranes. If you go to other companies and get other ion exchange membranes, they will have similar or perhaps lower levels of water uptake, but not much that's much higher than this. The second thing to note about this is that the water uptake in these membranes depends on the concentration of salt in the solution in which the membranes are soaking. And as the concentration of salt that the membranes are soaking in goes up, the water concentration gradually goes down. And this is the phenomena of osmotic deswelling. That is, as you increase the salt concentration in the water, it's actually lowering the water concentration in that solution and lowering the thermodynamic activity of water in that solution. And if you lower the thermodynamic activity of water in the solution, you have to lower the thermodynamic activity of water in the membrane that's equilibrated with it, and that means that the water content has to go down at high salt concentrations. We'll see how this plays out a bit later here. Now, the presence of these fixed charge groups, little purple dots here, are trying to represent, on the backbone of a cross-linked polymer network, are trying to represent, for example, sulfonate groups. And we imagine that we have a membrane as shown on this slide, and we immerse it in a solution of, for example, sodium chloride, an aqueous solution of sodium chloride. Now, this picture is not quite physically correct. These sulfonate groups on this polymer are never by themselves. They will always be balanced by a cation, and they might be balanced in, for example, by a proton, an H+. or by a K plus, a potassium or a sodium, etc. So there will always be a so-called counter ion. That is an ion that has a charge that's opposite that of the fixed charge. I haven't shown that here for brevity because I want to make another point with you. Now, the presence of these fixed charge groups, these negatively charged groups, is a powerful, it provides a powerful incentive for these positively charged sodium ions to try to sorb into this membrane. And at the same time, the presence of these negatively charged fixed charge groups provides a powerful inducement to repel the chlorides, or keep the negatively charged chlorides from dissolving in the polymer. And this is the phenomenon of Donnan equilibrium. And so what happens is, as you put this membrane into a salt solution like this, ion exchange will occur. So the membrane is hydrated, the ions are ionized and hydrated in the external solution, and by normal diffusion processes, the ions will start to migrate into and out of the membrane. The counter ions that are initially on this membrane can exchange out into solution, and over time, each of these negatively charged sulfonates will pick up a cation from solution, for example, a sodium ion, to remain electrically neutral. Additionally, there can be the sorption of a few of these chloride ions. The chloride ions are repelled by from the membrane by the presence of fixed charge groups of the same charge, but they're not entirely excluded. And this partitioning of ions like this is known as Donnan equilibrium. And what you can see is that at equilibrium, there's going to be an awful lot more positively charged mobile ions, that is, ions that are not bound to the polymer backbone. There'll be an awfully lot more positively charged ions in this membrane than there are negatively charged ions, and that's just to maintain electroneutrality in the membrane, so that the membrane has no net positive or negative charge. The presence of these fixed charge groups establishes an electrical potential at the membrane solution interface, and that's called the Donnan potential. And that Donnan potential acts to attract the positively charged sodium ions into the membrane and to repel the negatively charged chloride ions from the membrane. And so this is the point that I was making, that these fixed charge ions tend to exclude mobile ions of like charge, in this case the chloride ions. Now we will also refer to the salt or mobile salt in the membrane as the co-ions, in this case the chloride, plus their associated counter ions. And if you can imagine that there would be a concentration gradient, so that the sodium chloride solution on the left-hand side was at a higher concentration than that on the right-hand side, there'd be a gradient to drive salt through and across this membrane. And every time a chloride ion migrated from one side of the solution to the other, it would have to take a sodium with it to maintain electroneutrality. We really cannot violate in physical systems electroneutrality by very much. And as a result, we talk about mobile salt being the co-ions, that is, ions that have the same charge as the fixed charge groups, plus any associated counter ions. If a sodium wants to get out of this membrane, it has to go out in this picture. It has to go out it has to find a chloride to go out with. And what you can see just qualitatively then is, while there's a whole bunch of sodiums around, there are relatively few chloride ions, and so for salt to transport from one side of this membrane to another, it's going to be gated by how many chlorides are there, how many co-ions are there, and how fast they move. And that, in fact, turns out to be the case mathematically as well, as we'll see in a moment. Another way to look at this is in terms of the concentrations that one might see when membrane is equilibrated with a monovalent salt, so that the concentration of positive ions in the solution and the concentration of negative ions in the solution are the same, and both add up to give the concentration of salt in the solution. So for example, a 1 molar sodium chloride solution has a mole of sodium ions and a mole of chloride ions. And so these ions partition between the aqueous solution that's on either side of this membrane, and they partition into the membrane. And if the membrane has negatively charged sulfonate groups, then there's going to be an awful lot more positively charged ions, mobile ions in the membrane than there are negatively charged ions. Of course, if these fixed charge groups are positively charged quaternary ammonium groups, then this situation is going to be flipped. There'll be a lot more chloride in the membrane than sodium. And we're going to start to refer to counterions as being mobile ions that have the opposite charge of the fixed charge group. So that'll be sodium in the case of membranes that have a fixed negative charge like these sulfonate groups. And the coions are mobile ions that have the same charge as the fixed ions. So in the case of sodium chloride sorbing into a cation exchange membrane, that is with the sulfonate groups, the coions are going to be the chloride because they have the same electrical charge as the sulfonate groups. The reason we use the coion and counterion designation is that then when we flip from talking about cation exchange membranes to anion exchange membranes, we can use the same nomenclature, but in the case of the anion exchange membranes, the counterions are going to be now chloride and the coions will be sodium, exactly opposite from the cation exchange membrane with the negatively charged sulfonate groups. Now, the way we describe ion partitioning between the membrane and solution is exactly the way that you might imagine describing, for example, the partitioning of a gas like oxygen from air into water. We describe that by the ideas of equilibration of chemical potential. And in the case where the species may be charged, we have an extra term in the chemical potential expression that is related to the electrical potential of the phase in which the ions find themselves. And so this chemical potential is often called the electrochemical potential. You would recognize the standard chemical potential would be one involving just the reference term plus RT times the log of the thermodynamic activity of the ions. And then if the ions are charged, there will also be this term that represents the contribution of the electric field to the electrochemical potential of ion I. Again, Zi is the valence of the ion, F is the Faraday constant. A sub I is the thermodynamic activity of the ion, and this gives, like it does in uncharged systems, this just gives the concentration dependence of the electrical potential, chemical potential of ion I. So as the concentration of ion I varies, what does that do to its electrochemical potential? It's exactly the same definition as you would find in uncharged solutes, for example, like water partitioning into a polymer or oxygen partitioning into air. Now, when a membrane is equilibrated with ions in solution, at thermodynamic equilibrium, the electrical potential of all of the counterions in the membrane is equal to the electrochemical potential of all the counterions in solution. And at the same time, the electrochemical potential of the coions in the membrane comes to be equal to the electrochemical potential of coions in solution. So these are just, I think, would be intuitive representations of thermodynamic equilibrium. Each different ionic species is equilibrated across the membrane. Now, historically, counterions are represented by this subscript G, and that means Gegenion comes from the German words for counterion, and so we'll use the G here because that's traditional in the field. Now, what's often done is the electrochemical potential of all of the ions, counterions and coions in the membrane, is summed up and set equal to the electrochemical potential of all of the ions in solution. And if you take the expression shown at the top of the page and plug it into this expression, you get a remarkably simple expression. It's the one shown here. And it says that the product of the thermodynamic activity of the counterions and the coions in the membrane is equal to the product of the thermodynamic activities of the counterions and coions in solution. Now, I'm writing these expressions for a monovalent ion like sodium chloride partitioning into a membrane. In the article that's shown at the bottom of this slide, you'll find the equivalent expressions for other salts. Now, as we typically write activities, thermodynamic activities, in terms of activity coefficients and concentrations. We do that in uncharged solutions, gases, and solids when we're measuring partitioning between phases, and the same is done here. And so the activity of counterions in the membrane is written as the activity coefficient of counterions in the membrane times the concentration of counterions in the membrane. And likewise for the coions. The same procedure is used for the thermodynamic activity of counterions and coions in the solution, with one caveat, and that is that historically one writes the activity coefficient of ions in solution in terms of a so-called mean activity coefficient, and that's because one can't determine gamma plus and gamma minus in solution individually. The same thing is true actually for the membrane case, and so these ion activity coefficients often come together. Now, this is the condition, in this red box is the condition for thermodynamic equilibrium of ions between a membrane and a solution phase. There is another fundamental principle, fundamental law that has to be obeyed, and that is a charge balance in the ion exchange membrane. Now, you'll remember that the membrane had fixed charges on its backbone, and we're going to call that CAM. That's the fixed charge concentration. It will be the moles of fixed charges per liter of water sorbed into the membrane, or the traditional units. And a charge balance would say that the number of counterions in the membrane has to be exactly equal to the number of fixed charges in the membrane. Remember, you need one counterion to balance each of those fixed charges, one sodium to balance each of the sulfonates in the cation exchange membrane. And then if there's been any coion sorption, like chloride sorption in the membranes, you need a counterion to balance that as well. And so the total number of counterions to maintain the membrane electrically neutral is equal to the fixed charge concentration plus the coion concentration. You can solve these two equations simultaneously. You get a quadratic equation, and that can be solved for the coion concentration in the membrane, and it depends on the fixed charge concentration and the external salt concentration, and gamma, which is the ratio of the activity coefficients of ions in solution and in the membranes. And this is the fundamental expression for Donnan equilibrium. You'll find this called the Donnan equation in some parts of the literature. Now, with that picture in mind, we can start to talk about experimental data. And so, in that styrenic cation exchange membrane, it has sulfonate groups on the backbone of it. This is showing ion sorption or ion equilibrium data, where the ion concentration in the membrane is being plotted as a function of the external sodium chloride concentration. And so what's happening here is that these styrenic cation exchange membranes are being soaked in sodium chloride solutions of different salt concentration, and then by several experimental techniques, one can then go in and count or measure how many sodium ions are in the membrane at equilibrium and how many chloride ions are in the membrane at equilibrium. Those values are plotted here. And what you can see is that the sodium ion concentration is almost constant in the membrane. It rises just a little bit, but it's hard to see on this double log plot. The chloride ion concentration, on the other hand, starts out very low, and in fact starts out, almost 4 orders of magnitude, or maybe more than 4 orders of magnitude lower than the sodium concentration in the membrane. And then as the external salt concentration increases, the chloride ion concentration gradually comes up. And this is the phenomenon of Donnan partitioning. At very low salt concentration, those chloride ions, which have the same charge as the sulfonate groups on the backbone of this polymer, just have no thermodynamic interest in partitioning into that polymer. And as the external salt solution increases, then of course the electrochemical potential of the chloride in the external solution, as well as the sodium, increases, and that gives the chloride more opportunities from an energetic point of view to partition into the membrane. Now, if you do the exact same experiment on an anion exchange membrane, so it has quaternary ammonium groups on the backbone, the data look qualitatively similar, except now the sodium and chloride have flipped roles. Now the anion exchange membrane has as fixed charge groups quaternary ammonia, or positively charged groups, and now the chloride is the counterion. It's present in high concentration, and the sodium is the coion. It's excluded from the membrane by so-called Donnan exclusion. In the next slide, we're going to focus just on these coion sorption data, because that's the data that we have the expression for here in the Donnan equilibrium. We'll come back and include the counterions once we've dealt with the coions. Now, one of the classic failures of the Donnan model is shown here. So these are the experimental data. This is the Donnan model up in the upper right-hand corner. And historically, throughout the literature, people set this ratio gamma equal to 1. That is, they set the ratio of the activity coefficients in solution in the membrane equal to 1. And there's been a number of lines of reasoning for this, that, well, the membranes are hydrated, so maybe the membrane activity coefficients are about equal to those in solution, or the solutions aren't terribly non-ideal, so maybe they aren't in the non-ideal in the membrane as well. And you almost always see deviations between the experimental data and the Donnan model, and this is often used by people arguing that the Donnan model fails and that there's something wrong in the underlying assumptions. Now, what I'm going to try to convince you of is that this isn't necessarily the case, but that what has happened in the literature is because people don't take account of the thermodynamic non-idealities, they see significant deviations of the model from the experimental data. And if you can't predict the ion sorption, at the end of the day, it's going to be really hard to predict ionic conductivity, important in applications like electrodialysis, or ion permeability by concentration-driven experiments for reverse osmosis. So these deviations are important and have a meaningful impact on prediction of properties for actual applications. Now, as engineers, you might say, well, I can, one thing's for sure, we measure and know for a long time the activity coefficients of ions in solution. These are reported in handbooks. And so we can look those up and we say, well, we'd include the effect of the ion activity coefficients in solution and just set these ion activity coefficients in the membrane equal to 1. And it turns out if you do that, then you get even poorer agreement of the experiment with the model. And so that doesn't work. And what I'm going to try to convince you over the next few slides that what's been missing in this picture is proper accounting for the ion activity coefficients in the membrane. Now we can take the expression for thermodynamic equilibrium, which I showed you a few slides ago, write the activities in terms of activity coefficients and concentrations, and we can reorganize that as shown here. And this has the product of the counterion and coion activity coefficient in the membrane. They always come together. We can't measure them independently. And it depends upon the activity coefficients of ions in solution, which is, you can look up in a handbook, the concentration of salt in the external solution, which you set in the experiment, and then you can measure the concentrations of counterions and coions in the membrane. So everything on the right-hand side can be measured. And we can calculate what would be the value of the activity coefficients that would enforce thermodynamic equilibrium. And that's what's shown here. First of all, I'll show the mean activity coefficient squared for sodium chloride in solution. So this is just an aqueous solution. And you can see it's a long ways from 1. One of the postulates in the literature for Donnan, ideal Donnan behavior was that these activity coefficients equal to 1. Well, in fact, they don't. In the membrane, the product of the activity coefficients is on the order of 0.1, and it rises, so it has the opposite concentration dependence as it does in solution. Now, what does it mean for an activity coefficient to be greater than 1 or less than 1? If an activity coefficient is greater than 1 in this scenario, it means that the ions prefer to partition into the solution relative to the membrane. And if the activity coefficient is very much higher than 1, it means you'll find most all the ions in solution and very few in the membrane. On the other hand, if the activity coefficients in the membrane are on the order of 0.1, it means there is a really powerful thermodynamic driving force for the ions to be dissolved in the membrane. And what's driving this is the electrostatics. Those negatively charged groups in the cation exchange membrane really attract counterions. The counterions would much rather be in that membrane than in the external solution, and their activity coefficients reflect that. On the other hand, in the anion exchange membrane, which is positively charged, the counterions there are chlorides, and they really want to be in there next to those positively charged quaternary ammonium groups. And so it is the electrically charged, the charged nature of these materials that drives these activity coefficients to be so far away from 1. Now that gamma term previously was the ratio of these two activity coefficients, and you can see at low concentration that's on the order of 10. And so it's a long ways from 1 as was assumed in the ideal Donnan model. And we think this is the cause of the breakdown in the Donnan model to describe ion solubility into ion exchange membranes. Now, there have been no theories for predicting these ion activity coefficients, or no first principles theories, I should say. However, the trends in the concentration dependence of these activity coefficients are consistent with those observed in polyelectrolytes that are in solution. And the idea here is that ion activity coefficients for polyelectrolytes, so these will just be low concentrations of charged polymers that are not cross-linked but are just dissolved in aqueous solution. And they're sitting there perhaps with excess salt added to the solution. Ions are exchanging with the fixed charge group on the backbone, and the presence of these poly ions, polycations or polyanions for cation or anion exchange polymers, presence of these polyelectrolytes influences the colligative properties and the thermodynamic properties of the surrounding ions in solution. And there's been a lot of theoretical discussion about these, about this, the effect of the charged polymers on the ion activity coefficients of ions in solution. And so the question is, could we extend these to ion exchange membranes, which are like these polyelectrolyte chains, except they're cross-linked into solid materials that sorb water. And so here are the ion activity coefficients in solution around a sodium polyvinyl alcohol sulfonate polyelectrolyte. And you can see that they qualitatively follow the same trend as the ion activity coefficients that we observed in our ion exchange membrane. And so that motivates us to look towards the polyelectrolyte field for theoretical concepts that can be used to describe ion activity coefficients in charged membranes. One of the most famous models in this field is by Gerald Manning, and it's called the Manning counterion condensation model. Manning published this model in 1969 when he was a postdoc at a university in New York City, on his way to a faculty appointment, and it had a very simple picture for the way fixed charges on the backbone of a polymer chain influence ions in their vicinity. Manning took a very simple model of a polyelectrolyte as an infinitely thin line charge. So you imagine a polymer chain as just an infinitely stretched out piece of thread. That's the black horizontal line. And then every so often there would be a red dot, and that represents a fixed charge group, a sulfonate group, a quaternary ammonium group, what have you. And in Manning's model, these fixed charge groups were exactly spaced apart from one another, and they were repeated infinitely both to the left and to the right. So the distance between fixed charges in the Manning model is B. It's called B in his modeling. Now, this model has one parameter in it, and it's the so-called Manning parameter, which we write by the Greek symbol xi, and it is a ratio of two length scales. You'll see B appearing in the denominator of this expression. The top of the expression is lambda sub B, and this is the so-called Bjerrum length. And if you imagine that you have a fixed charge sitting out by itself, and there are counterions around it that if a counterion is very close to that fixed charge, the electrostatic interaction between this counterion and the fixed charge, for example, a sulfonate and a sodium, as the sodium gets closer to the sulfonate, the electrostatic force or interaction between them goes up enormously. And at some distance of separation, if the counterion gets very close to this fixed charge, the counterion will be trapped. It can't diffuse away from that fixed charge. It doesn't have the thermal energy to diffuse out of the region of electrostatic influence of that fixed charge. The Bjerrum length sets that sphere of electrostatic influence of a central fixed charge, and any counterion that's within that Bjerrum length doesn't have enough thermal energy to just to diffuse away. Bjerrum length, it turns out, can be written in terms of a number of fundamental constants: electric charge, dielectric conductivity in a vacuum. K is Boltzmann's constant, T is temperature, and epsilon here is the dielectric constant of the medium surrounding this fixed charge. We'll see how to calculate that here in a moment. Now, Bjerrum, imagine this picture that I've just described to you, that if you had like a cation at sitting in solution, and there were anions around it, that if those anions got within a distance of the Bjerrum length, that they would not be able to diffuse away. And in water, the Bjerrum length is about 7 angstroms, just to put things in perspective. The dielectric constant of water is about 78.5, and then that fixes the Bjerrum length here at about 7 angstroms. If you have media of different dielectric constants, then the Bjerrum length, of course, will vary. It turns out most polymers have dielectric constants down in the region of 5 to 10. And when you mix polymers with water, then you get dielectric constants in between that of pure water up around 80 and that of polymers, and that affects the Bjerrum length accordingly. Now, we come back to the Manning model again, and we can imagine a case where a bright polymer chemist comes in and puts additional fixed charge, makes a polymer that has the fixed charge groups closer together. And this is showing a scenario where the distance between fixed charges is just equal to the Bjerrum length, and that would correspond to a value of the Manning parameter equal to 1. Remember, it was a ratio of 2 length scales, this Bjerrum length to the distance between fixed charges. Now, there is the next case is the one that's of interest to us for ion exchange membranes, and this is where you have a lot of fixed charges on that polymer backbone, or they're spaced very closely together. And this is showing a case where the distance between fixed charges is half the Bjerrum length. And you'll see in a moment that this is the case that's of interest for most commercial ion exchange membranes. And so this gives a Manning parameter value of 2, because the Bjerrum length is twice the distance between fixed charges. And now you have these regions where the electrostatic field from one fixed charge group overlaps the electrostatic field from its neighbor. And in this region of overlapping electrostatic fields, any counterions that are caught in here are really doubly caught between these ions. They're experiencing the electrostatic attraction from both of these ions and have a really hard time diffusing out of this area. And Manning would say that these ions that are trapped in these regions of overlapping electrostatic field are condensed, and he calls, and that's because they're really restricted to staying very close to the polymer backbone, and just don't have enough energy to get to diffuse away from it. And so those ions are called condensed in his model. Now, he did allow for the fact that these condensed ions, while they don't have a lot of opportunity to leave, or it's a very low probability that they leave the vicinity of the fixed charge groups in this direction, they can go along the backbone of the polymer chain with relatively low energy. And you can think about this as a hiker hiking down a valley with steep mountains on either side. So, you can hike down the valley, but to climb up out of the valley and over the top of the mountains requires a large input of energy. And so you want to think about this in kind of an energy landscape point of view. Now, with this picture in mind, Manning developed expressions for the Gibbs free energy for the remaining uncondensed ions. And once you have an expression for the Gibbs free energy of these ions from statistical mechanics models, then it's fairly straightforward. We're not going to put you through that here in class, but it's fairly straightforward to go from expressions of the Gibbs free energy of the ions in solution to their activity coefficients. And so Manning's model provides expressions for the activity coefficients of the ions in solution. And that's why we're interested in using it for predicting ion sorption in these materials. Now, I'll just show the expressions for two cases. One for monovalent ions where Manning parameter is greater than 1, which is when counterion condensation can occur, and when it's less than 1, where counterion condensation cannot occur. And it turns out that these activity coefficients depend on the fixed charge concentration in the membrane, the coion concentration in the membrane, and the Manning parameter. And we can now come back to our Donnan expression for coion concentration. For the ion activity coefficients in solution, we can look those up in a handbook. We often compute them with a model like the Pitzer model that is very well represents the non-ideal behavior of the ions. And then we have the Manning model to calculate the ion activity coefficients in solution. And again, it relies on one parameter, the so-called Manning parameter, which is a ratio of those two length scales that I just showed you. Now, from the polymer ion exchange capacity in, for example, the styrene divinyl benzene styrenic cation exchange membrane with sulfonate groups on it, from the ion exchange capacity, we can calculate the relative number of divinyl benzene units to styrene, sulfonated styrene units. And if we stretch this material out in a planar zigzag conformation and assume that the projected length of the monomer is about 2.5 angstroms, we can calculate the distance between fixed charges just based on the geometric arrangement of the ions, and it turns out to be about 7.3 angstroms or 0.73 nanometers. So we can estimate what that distance between fixed charges is. Remember, the Manning parameter is a ratio of two length scales, the Bjerrum length and the distance between fixed charges. If we know the polymer chemistry, and we can estimate this distance between fixed charges. It also depends on the Bjerrum length, and we can plug in the fixed constants to get the expression that's shown here in the middle of the page for the relationship between the Manning parameter, dielectric constant in the medium, and the distance between fixed charges, B. And we can use a really simple model for the dielectric constant in the water-polymer mixture. That is just the volume fraction of polymer times the dielectric constant of the polymer, and that's on the order of 6. And then plus the volume fraction of water times the dielectric constant of water, which is about 78. And this will give us a measure of an estimate of the dielectric constant in the water-polymer mixture. And from that, we can calculate the Manning parameter for this styrenic cation exchange membrane. The only inputs we've had from experimental data to calculate the Manning parameter is the volume fraction of water in the sample, so we just measure that in the lab, and the distance between fixed charges. We know the polymer structure, we can estimate that just by simple geometric consideration. So this parameter is estimated from without recourse to experimental data on ion sorption. And so here's the data that I showed you earlier with first the Donnan model, assuming that the ions all behave ideally, and you see the deviation between the model and the experiment. And now this is the agreement when you combine the Manning model with the Donnan model and account for the thermodynamic non-idealities in the solution and in the membrane, we see much better agreement. There is still some disagreement at the lowest concentrations of salt, and we work now with Professor Manning and others to understand if this represents a breakdown in the model, and if so, what can be done to fix it. Once you get to very low salt concentrations, you can imagine the Manning model is based on a single polyelectrolyte, line charge with no other polyelectrolyte chains around it. Now, in these cross-linked ion exchange membranes, that's not the case. And we wonder if at low concentrations, neighboring polyelectrolyte, cross-linked polyelectrolyte chains start to see one another, and the ion interactions, the thermodynamic interactions for the ions are not modeled quite precisely by the Manning model. But over a wide range of concentration, it gives much better agreement than the standard Donnan model. And so accounting for thermodynamic non-ideality is important in these cases. Now, once you have a model that gives you the co-ion concentration, and so these are co-ion concentrations in the styrenic cation exchange membrane, and remember it's got negatively charged sulfonate groups, so this is the concentration of chloride in the membrane. Now, once you have that co-ion concentration, the fixed charge concentration, that is the number of fixed charges on the polymer backbone per mole of water, is determined by the polymer chemistry and the water uptake of the sample, both of which you know. So once you have a model for the co-ion concentration and you know the fixed charge concentration, now you can use the model to predict the counterion concentration. And so this shows the counterion concentration in both an anion and one of the cation exchange membranes, and shows a comparison between the model and the experimental data. What you'll see in both cases is that the external salt concentration goes up. You see very little change in the counterion concentration at low concentrations, and this is in a range where there aren't many co-ions in the membrane, and the water content in the membrane hasn't started to change much due to osmotic deswelling. But once you get up to higher salt concentrations, then you start to see the counterion concentration climb, and there's two reasons behind this. One is that as you start to get significant co-ion sorption in the membrane, you need counterions to balance those. So that accounts for part of this increase. The other is that you'll remember that the membrane was osmotically deswelling. It's losing water at high salt concentration. And this fixed charge density is moles of fixed charges per liter of water sorbed in the membrane. And so as the liters of water sorbed in the membrane go down, the fixed charge concentration goes up, and effectively the counterion concentration increases. You can also see that in these typical ion exchange membranes, the concentration of fixed charge groups or counter is about equal to counterion concentration at very low concentration, because there are no co-ions in the membrane. The concentration of fixed charge groups on the order of 3 to 3.5 moles of fixed charges per liter of water, and so there's an awful lot more higher charge density in the membrane than there is in the external solution, at least up and would be up until you get to very high salt concentration. Now, to understand if this model has validity with or generality, we compare it here to data in the literature for acid sorption, HCl sorption into Nafion. Nafion is an ionomer that has sulfonic acid groups, and it's been widely studied as a fuel cell membrane. Now, as a result of its importance in fuel cells, there have been very careful experimental studies of the dielectric properties of Nafion, as well as the distribution of fixed charge groups in the material. And so, based upon published values from spectroscopic experiments for the distance between fixed charges and dielectric studies for the dielectric constant, you can calculate a Manning parameter value of about 3.1. And if you do that, then you get essentially perfect agreement between the model and the experimental data. This is showing the data I showed you a moment ago between sodium chloride partitioning into now Nafion. and the value of the Manning parameter that was determined and really well fit hydrochloric acid data, that same Manning parameter gives great agreement with sodium chloride. And again, the ideal Donnan model gives poor agreement here. And then as you switch salts from something that's a monovalent to a divalent salt like magnesium chloride, using the same Manning parameter, you calculate the co-ion concentration, and it's almost perfect agreement. And I'm going to say that our teaching assistant in Rahul took these data for your viewing pleasure. And so we find one value of this Manning parameter can be used to describe the salt uptake in a given material can be used to describe the ion uptake of a variety of salts. We've measured a number of different salts in a variety of polymers and found good agreement between the measured co-ion concentration and the model-based prediction of co-ion concentration. We've also looked back over about 50 years and have found good correlations again between the measured mobile salt or co-ion concentration and the model values of mobile salt concentration. Now we're going to talk just briefly about salt permeability and ionic conductivity, and then pass on to a model of ion diffusion and combine that then at the end and get models for both salt permeability and ionic conductivity in charged polymers. I'm at about the limit of time for this lecture, so I'm going to stop this one here, and we'll pick up the lecture at this point next time. Thank you.